So we're in section 4.6. This systems of equations is a kind of a supplement to 4.6. It's right at the beginning of that section in your book. So I'm going to talk about systems and HL triangles. All right, so when we're talking about a system of equations, what we mean for what we're going to do is that we have two equations with two variables. So for example, we could have 2x minus 2y equals 8 and 9x minus 3y equals negative 6. So we have two equations. We have two variables. That's a system of equations. We're going to solve for most of what we do. There are three ways that we're going to solve them, but we're going to use mostly by substitution. We could also use elimination, or the third way that's not very accurate, we really don't use it, is we could solve by graphing. So we're usually going to use substitution. Sometimes we'll do elimination. So when we solve by substitution, the idea is to solve one equation for x or y. Doesn't matter which equation, doesn't matter which variable. We just pick one. Pick the one that seems the easiest. And then we substitute into the other equation. That's why we call it substitution. All right, so I'm going to go through an example, this example. So I'm going to solve the first equation. I'll do that in blue. 2x minus 2y equals 8. I'm going to solve for x, just because. You could solve for y, it doesn't matter. I want to get x by itself. So I'm going to add 2y to both sides. So I get 2x equals, these go away, and I get 2y plus 8. I could write 8 plus 2y plus 8, doesn't matter. I want to get x by itself, so I divide everything by 2, to divide everything by 2. So I get x equals y plus 4. Now I'm going to take this y plus 4 and I'm going to substitute it. This should be an x here. I'm going to substitute it into that first equation for x, because it says x equals y plus 4. So I'll do that in green. 9 times y plus 4 minus 3y equals negative 6. So I've substituted that into the other equation. And now I just have y. I can solve for y. So first I'm going to distribute. So I get 9y plus 36 minus 3y equals negative 6. Combine my like terms. 9y minus 3y is 6y. Now I want to get y by itself, so I subtract 36 from both sides. So I get 6y equals negative 6 minus 36 is negative 42. Now I divide by 6, and y equals negative 7. And now I'm going to take this, y equals negative 7, and substitute it right there to find x. So I get x equals negative 7 plus 4, which is negative 3. So my solution to my system of equations is x equals negative 3 and y equals negative 7. That would be my solution. Solve one of the equations for x or y, substitute into the remaining equation, solve for your variable, substitute, solve for your other variable. And we've done, this has come up quite a bit on the algebra review, so we've seen several examples of this, but we'll start seeing it more in our homework. All right, questions on that process? Okay, so if we graphed these two things, we could put each of these are equations of lines, we could put each of these in y equals mx plus b form, graph them. If we graph them, what this solution that we get, x equals negative 3, y equals negative 7, what that represents is where those lines cross, where they intersect. Well, when we have systems of equations, we can also have no solution. And that would happen if the lines don't intersect, if those lines happen to be parallel. You can tell that you have a no solution if you get an answer when you do substitution, like 0 equals 1 or 2 equals 5. Something that's impossible, something that's never true. So if you get an answer when you do your substitution, you get an answer like 0 equals 1, 2 equals 5, something that is not true, then you have no solution. Or you can get an infinite number of solutions. So those equations don't represent two lines, they're actually one line. And that doesn't mean that infinity is a solution. We're not saying that infinity is a solution, just that there are an infinite number of solutions. And you can tell that when you get an answer like 0 equals 0 or 2 equals 2. Something that's always true. So that tells you have an infinite number of solutions. All right. So systems of equations are going to start showing up a little bit more in our homework. So questions there. All right, now let's talk about HL triangles. Now, before we get into the theorem for HL triangles, I want to remind us all that we said before that SSA won't work for congruent triangles. And I'm going to draw a couple little pictures to show us why. Because, so I'm going to draw a triangle here that looks like so. And I'm just making these numbers up. I don't know that these numbers would actually work, but this is just as an example. All right, so we have these two sides of this triangle, this 5, the 8, and that particular angle. So those can't change. This angle can't change, this side can't change, that side can't change. The reason that we can't use SSA to say that two triangles are congruent is there is another triangle with this angle and these two sides that is not the same as this one. And here's how we can find it. I'm going to put my compass here, make it just the exact length of that side, and I'm going to swing it around here, and it's going to intersect the base of that triangle right here. So if I draw in that side right there, that length of side is also 5. So now I have this little green triangle, this one, and this big blue triangle, this one, that both have this angle, one side 8 and one side 5. And the green triangle and the blue triangle are definitely not congruent. We can get two triangles. Two different triangles. So that's why we can't use SSA. Except if I'm going to draw the same setup here, but I'm going to make my triangle a right triangle. So there's that same angle. We're saying that side's 8, that side's 5, and now this is a 90-degree angle. And now if I try to make another triangle like I did before, there's my compass. I'm making that, the compass open exactly 5. There's nowhere else that that side can swing around and connect with that base of the triangle. So we're going to say except if the triangle is a right triangle. And now we have a hypotenuse and a leg. And if we have another right triangle with the same hypotenuse and leg, it would be exactly the same. So that leads us to our HL theorem. So we can't use SSA because it's possible that we have two triangles that are different with the same sides and angle. So our HL, which means hypotenuse, leg theorem. And it's important to remember that HL is for right triangles only. So we're going to say if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and leg on another, and the other one has to be a right triangle too, then the triangles are congruent. So if we wanted to draw a little picture here, I'd have something like this, and I could do maybe something like that. We have a right triangle. We have two right triangles. And I can say, I'm going to call this D, E, F We have a hypotenuse and a leg congruent to a hypotenuse and a leg on the other right triangle. So I could say for my congruent statement, triangle ABC is congruent to triangle. Angle A has to match up with angle E. B would have to match up with angle F. EFD. So now we have another little clue that we can look for when we're working with congruent triangles. When you see a right triangle, you should think, maybe I can use hypotenuse leg. Now that doesn't guarantee that you can use hypotenuse leg, but right triangle suggests that you might be able to. Just like when you have a figure that has a diagonal section, diagonal piece, that you might be using the reflexive property. All right, I just want to go through a couple of examples using a hypotenuse leg, and then we'll be done with our lesson for today. So here's my picture. And we're going to be given that AD is congruent to CB. And let me, this is ADCB. And angle D and angle B are right angles. We want to prove that triangle ABC is congruent to triangle CDA. All right, so before we even start, what's one piece of information that might be very useful here? Just based on how I drew the drawing, yeah.
Line AC is congruent to itself.
Line AC is congruent to itself. So let's do our statement and our reason. I'm not gonna rewrite the givens, so those will go in here, and those are given. So we figured out, that's a good place to start. That's really the only piece of information that we can figure out, is that AC is congruent to itself. And what is that property? The reflexive property. And so with congruent triangles, we need three pieces of information. When we use hypotenuse leg, it kind of sounds like we just have two pieces of information, but really we have three, because we know that if we're using hypotenuse leg, we have a right triangle also. So do we have a right triangle here? Yeah? Do we have a hypotenuse? The hypotenuse is always the longest side or the side across from the right angle. Well, that's our hypotenuse. There's a leg. There's a leg. So we're done. We can say triangle ABC is congruent to triangle CDA by HL. And we're done with that example. All right, let's look at one more. Questions here? All right. So for this one, we have two triangles set up like so. And I'm going to say this is 3y plus x. This is y minus x. This is a 90-degree angle. X plus 5, y plus 5. And the question is, what values of x and y make the triangles congruent by HL. Well, for HL1, we need to check, do we have right triangles? Yes, we have right triangles. We have those 90-degree angles. So for HL, we need the hypotenuses to be congruent. So what's the hypotenuse on this left triangle? So we need 3y plus x, the longest side, the side across from the right angle, has to be equal to, congruent, the same. Hypotenuse on this triangle, y plus 5. We need the legs to be congruent. So y minus x has to equal x plus 5. Well, what a coincidence. We have a system of equations. And we need to solve for x and y. So I would choose, if I were doing this one, just because there are no numbers in front of the x's and y's in this equation, I'm just going to solve this equation for y. So I have y minus x equals x plus 5. I add x, and I get y equals 2x plus 5. So solve that equation for y. Now I'm going to take that, 2x plus 5, and I'm going to take it and put it in the other equation for y, there, and there. So I'm going to substitute. So I get 3 times 2x plus 5 plus x equals 2x plus 5 plus 5. So now we just have x's there. And I'm going to be able to solve for x, get x by itself. So we'll distribute. First, I get 6x plus 15 plus x equals 2x plus 5 plus 5 plus 10. Combine my like terms here. 7x plus 15 equals 2x plus 10. I want to get x by itself, get all the x's together. So I get 5x plus 15 equals 10. Subtract 15. 5x equals minus 5. Divide by 5, and x equals negative 1. And because we're talking about triangles, I want to check to make sure that this makes sense, that I'm not going to get a side that is negative. So if x is negative 1, this side is 4. If x is negative 1, I think we're okay. So I just want to make sure that I didn't make a mistake and have a negative side length somehow. Well, now I'm going to take this, x equals negative 1, and put it right there, and I'll get y. So we get y equals 2 times negative 1 plus 5. So y equals negative 2 plus 5 is 3. So my solution is x equals negative 1 and y equals 3. And that would make those two triangles congruent by hypotenuse length. The hypotenuses would be the same, the legs would be the same. Questions? Okay. Our homework is in 2 pieces. One is systems of equations. A couple of those. Oops, this should be 257 first. Number 2 through 8 even. Those are the systems. And then on page 262, these are the hypotenuse leg problems, 11 through 26.